Problem of the day, the simple pendulum. What's so simple about it? It's got a mass on a string. That mass is of negligible dimensions. The string is so light that its mass doesn't feature in the problem at all. So we have one mass along distance L away from the pivot point such that it has a moment of inertia of mr squared. We want to set this problem up as a differential equation, and to do that we're going to need to take a look at the net force. There are two forces on the simple pendulum. One of them is tension. That's easy. And you know it's not going to be the world's best day when the tension going on the diagonal is the easy one. The other one is the weight of the bob itself going straight down from the center of mass, which doesn't matter because we don't know or need to know the radius of this, and there is your FG. As is usual on the AP and all other advanced problems, breaking things into components in the Cartesian system is not going to get you anywhere, so don't try it. You have to rotate your three-body diagram, you have to rotate your thinking, you have to look at the two directions in this problem that are relevant, namely the centripetal direction, where the net force will change your direction but not your speed, and the tangential direction, centripetal component of FG, and it's pretty clear that if these two vectors aren't equal, then either your string is going to shorten and lose all the tension, in which case the problem is over and we need a new three-body diagram, or it's going to lengthen, and if your string is stretchy, that's an interesting Hooke's law problem, and if the string is not stretchy, it will break and you will have a simple projectile going down in no short order. So the net force is going to come here from the tangential component. Here is our tangential acceleration. Similar triangles, and the geometry exercise we did when we did the mass on an incline problem, the ramp, in first year physics, that these angles theta are similar. So there's our tension looking mightily like the normal force that ever was, and there is our net force. Giving no surprise to anybody. Now, every time we've done a differential equation up till now, it's been Cartesian, x, y, and t. We've never had to work with theta before. There's no point in setting this equal to ma, because a is your net acceleration. It's got a centripetal and a tangential component. It's not even in the same coordinate system as theta. It's not going to be the derivative of anybody. So we're going to have to sit down and find an equation that has a derivative of theta in it, and that has something more to do with this kind of motion than linear acceleration. Press pause and see what you can figure out for why this pendant is swimming back and forth. Problem, guys. We're not in the land of net forces and translation because the pendant didn't go anywhere. See? It's still right here in my hand. This is a torque problem. The pendulum underwent angular acceleration because of a net torque of F cross R. Now, we'll be really glad we spent all that time on the geometry finding out the parallel and the perpendicular components, because torque is a cross product. We want the perpendicular component of the force as drawn tail to tail with the radial distance that we carefully labeled L, going from here to there. Now, write out what the net torque is supposed to be, and then use Newton's second law for rotation to set it equal to the appropriate kind of acceleration, angular acceleration with the appropriate coefficient, and rearrange to form a differential equation. Get the problem as far as you can, press play to check your work. There's your torque, and there is Newton's second law for rotation with your angular acceleration all ready to go. Next step, get the acceleration by itself. You'll get a lovely collection of constants up here, and then trouble. The step after this ought to be writing the left side as a derivative of something simple on the right side. Acceleration, angular acceleration, is, as we all know, the second derivative of theta. Unfortunately, that's not going to get us very far. That wretched sign. We know how to solve a differential equation with a second derivative on one side and a variable on this side, that there is no calculus in the world that says what function has a second derivative that's equivalent to take the original function, take the sign of the original function, and jumble some constants out front. It just can't be done. However, if we look at what we did previously with the small angle approximation, we will see a way out. If you want to model an ordinary pendulum, a simple harmonic motion, you are simply out of luck. It's not simple. It's not simple at all. But if you want to make the restriction that instead of showing off your ninja skills, you keep the pendulum at a very small angle that's under your control, then you'll be able to say, sorry about the zoom there, that for very small angles, you can approximate that sine term as the original angle. Instead of that mess, you can look at the second time derivative of theta as measured from here to here. Notice that theta here is stretched on the left, which means that this theta is a negative number, while this force going to the right is positive. Alternatively, if you're not comfortable with negative theta, we can do the diagram over here, where theta is positive, and then the restoring force is a force to the left. Notice that either way, one way or the other, you're going to get the sign of the acceleration is opposite to the angle you're working with the same bunch of constants out front. Why could we do this? Why could we say that sine theta is approximately equal to theta? Only for small angles. How small? Let's get a formula, and you'll measure how small. But once we're here, we have a function whose second derivative is proportional to itself, only negative, and with some constants out front. Pause here. Now that you've got the differential equation, solve the differential equation, put in your boundary value conditions, see what theta initial was, see what the initial velocity was, box your answer, press play to check your work. Harmonic motion as ever we've seen it starts at some value with an initial velocity of 0. That would be cosine. Theta naught is whatever you set it as on the left or on the right, and the only thing that remains to be seen is what the coefficient of t is here. Last time we checked, that angular frequency should be the square root of whatever constants we're knocking around in front of the original variable in the differential equation. There, that wasn't. Now find what we came for. Find the frequency in hertz and find the period of motion, assuming you keep that pendulum restricted to small angles. Now, simplify. We said from the start that the moment of inertia was mr squared, where r was very clearly L. Simplify as far as you can go and box your formulas. Cross out all those like terms, and you'll get the formula for a period of a simple pendulum as printed for you on your AP sheet. Ask yourself, does the period of a simple pendulum held at small angles only depend on its mass? Why not? And if it doesn't depend on its mass, what's the only variable that ought to affect the period of the simple pendulum? You'll try this yourself in lab with a helpful sibling and a stopwatch. Please note that we have derived even pendulums that are not simple. If the pendulum is not simple, if it has a known length and width and breadth, if the mass of the string is not insignificant, the only thing that's going to change is here, the moment of inertia, and here, the radial distance from the pivot point to the operating point for the force of gravity. We know that the force of gravity always operates through the center of mass. So if the pendulum is a complicated pendulum instead of a simple one, you need to find the center of mass, find the distance between the center of mass and the pivot point, and you can get as far as here with the exact same effort you spent on the simple pendulum. An example of a complicated pendulum would be a torsion pendulum, something that is spinning in 3D, that's twisting around itself back and forth rather than simply going up and down. This is how most pendulum clocks and watches actually work. They are twisting the springs rather than just stretching them. Check it out. Give it a twist. Keep it at a small angle, and the torsion pendulum will twist back and forth. You can try it yourself on the playground with a tire swing. The torsion pendulum, with a moment of inertia I incorporating both its mass and all relevant lengths, as you twist it and untwist it from an angle of theta, can be summarized by a three-dimensional restoring force. Instead of spring constant K, for one dimension, we have a spring constant of kappa in 3 dimensions, such that if you twist with an angle that's going this way, the torsion pendulum will pull you the other way with a force proportional to the amount that you twisted. Try setting up a differential equation for that one. Happy trails!